So I have the pleasure to be the last speaker of today. I'm Philipp. I do my PhD in Bristol, and I just got into my fourth year, so I would like to present you the work we have done there. I worked there together with my both supervisors, James and Mike, on seismic anisotropy and deforming salt bodies. And before I start, I would like to say thanks to some people who helped us also with this work, Andrea and Chris, who gave us very valuable comments on the things we have done, and also Martin and Dan from Rockfield, who so that is my industrial partner in this project, and they made this collaboration possible, and also gave us very good feedback, basically. I would like to start with a quick motivation why it might be interesting to look at salt deformation from a seismic point of view. As you know, salt is involved in a number of industrial applications. It's, for example, used for storage of nuclear waste. It's also been used lately as an energy storage of compressed air, for example, in the subsurface. And another important property of salt is that it's often involved in forming hydrocarbon traps due to its very unique properties. So, and the idea of this project is that we, and in this due to the deformation in the flow, which might go on in these kind of settings. So I'll show you one sample of salt diapir on the bottom left. This might lead to a certain lattice preferred orientation. We got this idea actually picked up by studies which has been done on olivine, and which has been also discussed before, for example, by Lucan. And this, if the single crystals are seismically anisotropic, and as halite is seismically anisotropic on single crystal scale, then this would lead to effective seismic anisotropy on scales which might be important for seismic wavelength. And if we do not account for this effect properly, this might lead to wrong subsurface image. With that in mind, I would like to quickly, I talked about seismic anisotropy without really saying what it actually is. I imagine many of you know that, and we also have been heard many talks about that. So one phenomenon which we see in seismically anisotropic media is then when a shear wave is entering an anisotropic medium, it gets split in two different waves with two different polarization directions and velocities, which leads then to a time delay between this fast and the slow wave, which give us first an estimate about the amount of seismic anisotropy, basically, and also gives us insights into the deformation history by measuring the polarization of the fast shear wave. And on the right side, I just show you a P wave anisotropy surface calculated from the elasticity tensor of a single halide crystal. And you can see that the P wave velocity varies depending on the polarization direction. So that is another effect which we see there. Now I'd like to, we would first quickly give you actually like a further motivation by looking at a seismic data set we have, where we, from the Gulf of Mexico, we did measure quite clear seismic anisotropy. Then I would like to show you a geo-mechanical deformation model we have been developed in Swansea at Rockfield to apply our idea to link the deformation and the seismic anisotropy, as I explained at the motivation. And then I show you very quickly some seismic modeling we did and based on the velocities we have calculated, and then I will summarize everything in the end. So the mahogany salt body is, as I said, located in the Gulf of Mexico. So here you have an overview about basically the northern part of the Gulf of Mexico, and all this black stuff is salt, and you can see there's also like some faults, and the mahogany salt body is there indicated with this gray arrow on the right side. Hope you can see that. And the Gulf of Mexico is actually quite extensively like studied area, because like there's loads of oil and gas discoveries in the past. Just a very quick like closer view in the so you have an idea about the scale what we are talking about. Just a closer view of the mahogany salt body. We do have a VSP data set from there, which is so this vertical seismic profile data set. So that I show you how this schematically looks like on the left side, where we do have like a borehole through the salt, and the receivers are vertically aligned on top of each other inside the borehole, and we have a source somewhere far away from the receivers. And you can see that some of the receivers are inside the salt, and some of them are below of the salt. And then we look at the I show you the seismic response of the receivers on the right side. That is the P2S conversion at the top of the salt, and that is the P2S converted wave at the bottom of the salt. And as I said, we want to use shear wave splitting to measure the seismic anisotropy in these kind of inside there. So I just show you from one receiver how this actually looks like. Here already in the top panel rotated into so-called fast and slow direction, where we just have where the waveforms are more or less just separated by a certain time delay, which gives us an estimate about the amount of seismic anisotropy, which is about like 20 milliseconds here. And on the right you see the particle motion, which is for the uncorrected phase in the top right, which is basically just a plot of the components of motion against each other. And what we then do is basically linearizing this particle motion, and which then basically mimics an isotropic case, because the energy is just polarized in one direction. And we end up with having informations about the splitting parameters, which is as I said, the time delay between the fast and the slow shear wave, and the polarization of the fast shear wave. We do this for all of the receivers. So for all of the receivers we had, and we end up with something here. So on the x-axis, which I just showed the different receivers we had. So where one was at the like inside the salt, and 48 is already outside the salt, so it's the bottom. And on the y-axis you see the time delay between the fast and the slow shear wave, which is gives us an estimate about the amount of seismic anisotropy. And we can see that there's an increasing time delay with ongoing travel time through the salt, which is basically a very clear sign of seismic anisotropy. So we had some problems with wave conversions from the salt to the shale layer beneath. For that reason, we had some very suspiciously high-looking time delays, which I didn't show here. So from receiver 11 to like 13 to 24. I said we then we did try to build a deformation model of the Gulf of Mexico, or like not of the Gulf of Mexico, of the mahogany salt body in the Gulf of Mexico. That is what I did in my time at Rockfield, and we did basically a very simple setup. So we didn't want to have like too much complexity inside the model. We didn't want to have like too much. And we did constrain the properties with quite typical Gulf of Mexico properties, which applies to the rheology of the salt, as well as the general geometry, as well as the compression rates, for example. Just to show you very quickly how it evolves in time. So in total we have 5.8 million years of salt deformation. So you see this 2D model, and it's quite we kept it quite simple. Obviously you can put more complexity in it. So what is the mahogany salt body is effectively like an advancing salt sheet, and we did pick up the geometry by a seismic restoration paper from Mark Rowan. So I show you a picture of them on the right side there. What they did is basically they interpreted seismic horizons together with like biostatic data to come out with an idea how the mahogany salt body did evolve in time, and that is based here just in 2D along one seismic profile. And on the left side again our model. So in the very bottom right you see how the mahogany, how they interpreted how the mahogany salt body looks right now. As I said, we want to link the deformation inside these kind of settings with the possibility of seismic anisotropy occurring. For that reason, so to do that, we estimate strain along certain kind of path lines inside the model. So we applied this idea to the mahogany deformation model I just showed you, where so here the red dots are just we trace particles through the model in time, and the red dots just show where they are at the very end, and the blue line just showed one specific point which we have traced in time. And then we just calculate very straightforward the change of the deformation velocity in space direction. Shown on the right side there, where in our case we don't have any. We just have a 2D case in our sample, and we use this as an input in plasticity texture modeling program. In our case we use VPSC, which has been already introduced by previous talks, for example by Lucan. And just to remind you how this works, you basically try to predict the crystallographic texture in our case of polycrystalline halite. So we assume that our whole salt body is just consisting of halite when a certain kind of deformation has been applied. And so that example is not related to what I showed you before. It's just an example of, at the bottom is just the texture of a compression experiment have performed in Utrecht, where they have compressed a polycrystalline halite, and we had tried to simulate this texture with VPSC shown at the top. Important to mention is, as I pointed out already, this recrystallization is not considered in VPSC, which will certainly have an effect on the microstructure. Just one example, one more example of how the example of how the texture evolve for basically this blue line I just showed you a couple of slides ago. So along one certain path line, here for different kind of time steps from 1 million year to 5.8 million years for a certain set of input parameters we used for for the single crystalline properties of halide. And so we do this stuff for all of the points, and I promise to say something about seismic anisotropy. So we come up in the end, if we do all that for all the points, with something like that, where we calculated the based on the texture, we have calculated the seismic anisotropy on the left side for the P waves, and on the right side for S waves. Here just giving as a percentage, and so that is again based on the geometry I showed you before on the mahogany deformation model, without this diap here, so without this source we have seen. So what we can see is that like first we get quite high values of seismic anisotropy. In P wave we end up with having values up to 5%, and in S waves up to 10%. And we also see that we do have a quite high amount of deformation. Where we do have a high amount of deformation, we also have a high amount of seismic anisotropy. We then went one step further, and we tried to use the calculated velocities we had for some seismic modeling, which I show you the results here. Again, so the geometry should be familiar now with you. So that is again based on the deformation model I showed you before, and the gray stuff is just isotropic shale in our case, and the black is the salt body, where we inputted the seismic velocities as calculated with the plasticity models, where we had the effective elastic properties calculated with that. And we wanted to have something similar than in what we had in our VSP dataset. For that reason, we put the receivers at the right side there, with this where the green line is. So these are again 48 receivers, which have similar geometry than we had in the VSP dataset. So also the first 12 receivers are inside the salt, and the rest is beneath. And what we then did is, in a next step, we basically processed the synthetic data in a very similar way as we did for the VSP dataset, and we end up with so we again calculated shear splitting results, and try to estimate the time delay between the fast and the slow shear wave, which we measure between of the seismic anisotropy, and we end up with quite a nice match between the delay times, especially at the receivers, which are below the salt, which should just give us the most stable results. Obviously, this doesn't mean that the anisotropy we see in the mahogany salt body needs to be due to crystal alignment, but our synthetics match with that quite well. So what I've talked about today, I first showed a new idea, a new workflow to link deformation with seismic anisotropy, and we applied this to one specific salt deformation model. We do see that we have quite a high influence on seismic waves, which about 5% in P waves and 10% in S waves, which would certainly be enough to significantly distort seismic images in the subsurface. And we also see that our synthetics matched quite nicely with what we see in the VSP dataset. And and also we had showed you at the very beginning of the talk that the mahogany salt body, we measure quite clear seismic anisotropy inside the mahogany salt body. So basically to conclude everything, I think it's not yeah, and often in seismic processing, salt has been considered to just be isotropic, and I clearly think that is not the case. And yeah, I hope with something like that we can like push it a little bit more in that direction, that we can investigate further along those lines. So yeah, thank you very much for your attention.